All right, so thank you again. Hello again. And let me put the Jamboard link in the chat box. I can see the chat box, so don't hesitate to harass me with questions. All right. And I'm going to continue on what I said yesterday. So remember that we are continuing section 2. So section 2 is about defining F structures and looking at collapsing constructions. And all of this is due to Cheeger Gromov. Let's see. Yeah, maybe a quick summary of what we did last time. So last time we saw that in order to study the minimal volume and similar invariants, what you really need to understand is the thin part. That's the difficult part. That's the non-trivial part. But to understand, volume or essential mean vol, you need to understand the difficult part, which is the thin part, where the injectivity radius is very small. Because if you're given a manifold with a bounded sectional curvature, so you have two pieces, and the thick part is completely okay by Cheeger, right? Okay, by Cheeger, meaning any topological information or geometric information about the thick part is just upper bounded by its size, meaning by its volume. And that's not true for the thin part. But the thin part is very well described by this far-reaching theory of Cheeger, Fukaya, Gromov. By Cheeger, Fukaya, Gromov theory. And today what we're going to see is the first step, one of the first steps towards understanding something systematic about the thin part, which is going to put a first structure called F structures. So yesterday I was, at the end of my talk, I was giving you an example of some basic collapsing construction. And let me come back to that for a second. So first, let me also correct something. I don't think I said it out loud, but in that trick, so the rescaling along a killing field trick, you really want the killing field to be nowhere vanishing. Okay, so I'm going to add that here. K is nowhere vanishing. So that corresponds to the fact that the generated R action is actually locally free. So it locally does not fix any point, right? And that's necessary in the proof in order to find these very nice coordinates where you can compute your metric and see that actually the curvature is bounded when you rescale the metric along these killing fields. And let me remind you that this trick extends to the situation where you have multiple killing fields that are nowhere vanishing and that are also commuting. All right, and I was talking last time about this example where you look at 0, 1 cross R2 and then you do something. So let me restart this example because I don't think this is the killing field I want to see. So this is a nice killing field, but there's simpler. So let me, I can't create more frame. All right. So, So sorry about that. You know what? I'm just going to use not use Jamboard. So today, for let's see. Okay, sorry about that, but today Jamboard, I didn't know there was a limit on the slides, and it's too complicated. So let me just continue on my just notability. Okay. All right. So example of last time. So you are considering the quotient of 0, 1, or 2 flat by a certain rotation. So let R theta be the rotation of R2 centered at 0 of angle theta. And then what you impose is that such a point is equivalent to the point that is defined as follows. And all right. So let W be the 0, 1 coordinate. And let the killing field be just simply this vertical constant vector field. And you can apply the rescaling trick by rescaling the metric along that killing field. And when the angle is 0, then the situation is very simple. You have metrically a product, so a product metric of flat metrics on S1 and R2. So as delta goes to 0, delta being this parameter in the rescaling trick, right? As delta goes to 0, then your Gromov-Hausdorff limit, pointed Gromov-Hausdorff limit is going to be the flat R2, right? So when theta is irrational, it's a little bit different. So say R1 over M2, if you're rational, but you're not 0, then in general, you're not a flat R2. So if you think about this, let's see. So you have the two R2s, and you have 0, 1. That's this, one of the slices. And if you take a point, what R theta is doing is that it's, let's say, so that's the killing field. And because along the killing field, the metric is going to be smaller and smaller and smaller, in the limit, you can identify these 2 points. So these endpoints of the this pink segment that I draw. But the top point here is identified because of the rotation. It is identified with a point on the first slice that is rotated by theta, okay? So this green point is going to be identified with that point in the quotient. So what I mean is that from this picture, you can then see that the Gromov-Hausdorff limit in a pointed sense is going to be an orbifold. So it's going to be R2, but with a conical metric. So it's not exactly conical, but the infinitesimally, the angle at this singular point at the tip is equal to 2 pi over M2. So you see that limit of flat manifold doesn't really have to be a manifold. And even more drastically, you can look at what's happening when theta is not even a rational. Remember that bounded sectional curvature. So as as delta is going to 0, the curvature is uniformly bounded by the rescaling trick. And now suppose that theta is irrational. That means that if you look at, again, this picture that I'm trying to draw, if you look at the following torus, then the killing field is going to become dense in this torus, etc., just because theta is irrational. But that means that your whole torus is going to collapse, and then the limit is going to be one-dimensional. In fact, here the limit is going to be something like half a line. So I do not care about the metric here of the Gromov-Hausdorff limit. I just want to give you the homeomorphism type of the Gromov-Hausdorff limit. The metric is going to depend on your theta. And it's not necessarily the flat metric. So that is my examples, and let's go on. Let's move on. Okay, so F structures of Cheeger and Gromov. So this is the structure that we want to understand, and that's going to largely include all these small examples that I described. And in order to define what an F structure is, let me first describe what an elementary F structure is. First, let's define elementary F structures. So you take an open set U. What is an elementary F structure? It's given essentially by a virtual torus action. In the following sense, open. Like following. So you have first a finite cover of U, which is normal. Covering of U, such that the covering group, we're going to call it gamma. So gamma is in other words, the group of deck transformation of your covering space. And then secondly, you want to assume that there is a torus action on U tilde. the covering space. You want a little bit more, so you need to first have an integer that's going to be the dimension of your torus, and also a representation of gamma inside the automorphism group of your torus of dimension k. So the automorphism group is just SLK Z, right? And you want that the following semi-direct product acts smoothly and effectively on the covering space. On first reading, you can ignore this representation thing, but just think of the situation as having a TK action that is effective on your covering space util. So now what we want to do is to try to find examples where you have an elementary F structure. In particular, I want to focus on complete flat manifolds because that's going to be our model case. On complete flat manifold, we will see that we can find such elementary F structures, and it's not too difficult. Well, let's do that. Let's put elementary F structures on flat manifolds, completely flat manifolds, because this case will serve as a local model. For the general case by a blow-up argument, simply. So let's remember just that elementary F structures in virtual torus action. Okay. I should recall something about compact manifolds. Recall that recall the theorem of Weber-Bar. Okay. Weber-Bar tells you what compact flat manifolds are. If you're a closed manifold of dimension n and you're flat, then you are finitely covered by a flat torus. Flat torus, and the degree of the covering is uniformly bounded in terms of the dimension. So this covering degree is bounded by something that I'm going to call lambda n. It's just a dimensional constant. And so in some sense, flat manifolds are essentially tori, right? And you can say something very similar for complete flat manifold, this time the non-compact case. So let's take a flat and complete manifold of dimension, say, let's say n. If this guy is flat and complete and non-compact, then first you can get rid of all the R factors, the trivial factors in your metric. I'm going to call xn as being the product, the metric product of xl with rk, where xl has no more R factors. Then the theorem of Cheeger-Gromov, is giving you the structure of this XL. And it says the following: it contains a unique compact, flat, and totally geodesic manifold. So unique sol, it's called a sol. Compact, flat, totally geodesic sol of lower dimension. So it's a compact submanifold such that XL is nothing else than a flat bundle over this SM. Symmetric space of the normal bundle over S. And the simplest case that you can think of is the examples that I gave you, right? So you have, in the examples I gave you, you have a flat bundle over S1, simply. And S1 is playing the role of the S here. Okay, so notation-wise, it's not maybe the best. SM here has nothing to do with spheres, and it's a flat manifold. And in particular, by Bieber-Bach theorem, it's finally covered by a torus. All right, so it is on these kind of manifolds that you want to find elementary F structures. So how do you do that? On compact and flat manifolds, that's easy. So let S tilde denote this torus given by Bieber-Bach theorem. Okay, the torus covers finitely many times this compact flat manifold S. Given by Bieber-Bach theorem, then the torus action on this cover is simply given by the action of the torus on itself. We just look at the action of S tilde onto itself. On itself. And that is your elementary F structure. If you look at the definition of an elementary F structure, it's exactly that. So you already got an elementary F structure where the open set is just the whole manifold S. F structure. So that's not really interesting. What's interesting for us is going to be the non-compact case, because these non-compact flat manifold are going to be our local models. So non-compact flat manifolds, let's say XL as above. So let me assume that XL has no R factor, and XL is the isometric to a flat bundle over a flat closed manifold SM. First, what you can do to fix ideas is to make the sol be a torus. So you lift your manifold to a covering. Consider x tilde corresponding to the covering of S by a flat torus given by Bieber-Barth's theorem. And all right, now I want to give you a procedure to construct an elementary F structure. First, let's look at the fundamental group of XL. The fundamental group of XL is simply the fundamental group of the soul. And it acts by isometry on the universal cover of your original flat manifold X, which is the flat RL, so the Euclidean space of dimension L. And the action is simply by deck transformation on the universal cover in the usual way, right? You have a subgroup, actually a normal subgroup of this first fundamental group, which is given by the fundamental group of this covering space. And it's going to be the pi1 of the soul. This I'm going to denote it by delta, and delta is simply z to the power m, right? So it's a abelian group, and it acts also by isometry on R. Similarly, that's isom on RL. Now, it will take some time before I come to elementary F structures, but if you take any element phi in this abelian group, it determines a one-parameter family of isometries, Pt. Isometries that I'm going to call phi. For instance, if phi is equal to translation up by a vector w and rotation in the if say if phi is equal to that isometry, so that isometry it just means you vertically translate by w and you rotate by theta. Okay, you rotate by theta in the plane that is horizontal. So I'm claiming that this defines a one-parameter family of isometries. You just define T as equal to be TW and RT theta. All right, so you're just interpolating between identity and phi in this natural way once you write it as the combination of a translation and a rotation. One thing to realize is that this map from this abelian group delta to this one-parameter family of isometries doesn't have a group structure or something, in the sense that, okay, if you have two elements that are, one is the multiple of another, that does not imply that the corresponding one parameter families are multiple of one another. That's something that one should understand. And one simple example is when you look at the following situation where phi is the translation by 2 in the vertical direction, and it doesn't rotate. Let me first write this down. And C is going to be equal to translation by 1 vertical direction, and you rotate by P. In that case, Pt is equal to 2t R0. R0 is the rotation of angle 0, is the identity, but on the other hand, Ct is equal to something t, and you need to rotate. So as time evolves, as t evolves, you're rotating more and more, right? And so that's an example that shows you that you should be careful that you don't have the property that phi t is equal to k times ct or something. So why phi could contain a rotation part if, okay, so that's a good question. So phi could contain a rotational part because you, the quotient of RL by Zm is not compact, right? So for example, you can think of just Z as being the group, translate by 1, rotate by P. That generates a abelian group. It's a cyclic infinite group. Maybe so the confusion might come from the fact that indeed, if you are in the Biber-Bach situation, so if you have a abelian group Zm and you quotient Rm by Zm, all those Zm are going to be translations, so no rotational parts. But here, again, you're looking at a compact flat manifold, so it's just a non-compact flat manifold. It's a flat normal bundle over a compact flat manifold. And you could just have, a bunch of isometries with rotation, non-trivial rotational part that generate a Zm. Always in these examples, I like to keep in my mind this those trivial example where that I gave you earlier. So those flat bundles over S1 with different angles, and you can try to imagine in those situations what everything is doing. All right, so that whole remark was saying, given any element of this abelian group delta, you get automatically by interpolation a one parameter family of isometries. And now, if you're given multiple elements, you get multiple families that are commuting with each other. That's the second remark. Remember that delta is the fundamental group of your torus, the sole torus. Okay. So you get R different one parameter families. Of isometries commuting with each other. So actually, when you think about that, you get a torus action on the quotient by Zm. On the quotient, which is equal to L that you quotient by the action of delta. Is that clear? So you see that, okay, if you give me some elements of this CM, you can cook up a torus action on this cover of your original manifold X. That's something good. Unfortunately, in the definition of elementary F structure, you need some compatibility condition with the deck transformation. You don't just want to have a torus action, you want a torus action that somehow respects the deck transformations. That's why there were these semi-direct products. So let me make the following assumption that we will be able to make it satisfied, but let me suppose star. So star means that this family of isometries is invariant by conjugation by any element of the fundamental group. So is invariant conjugation by elements of the biggest fundamental group, so the fundamental group of your original manifold. Then it's an exercise then to show that there exists an induced representation. There is induced representation rho from the quotient pi1, pi1 of what? Pi1 of your original manifold divided by this abelian part into the automorphism group of TR, which is just SLRZ. Once you have this, okay, notice that this is just the covering group of the covering, X tilde to X. X is your original manifold, X tilde has a abelian fundamental group, and you have this representation. And if you look at the definition, that exactly gives you an elementary F structure on X. F structure on X. So up until now, what I did was to give you a procedure and a condition to satisfy in order to find an elementary F structure. And we will see that we can always make this condition being satisfied. But first, an example again. And it's going to be, again, this famous flat bundle. Let's denote it by E theta. It's a three-dimensional non-compact flat manifold. And so if theta is the zero angle, then I remind you that E0 is just the product of S1 with the flat R2, so flat product. And then an elementary F structure on that exists. You just take the S1 action, the object S1 action. Nothing to see here. Take the S1 action. Not much to say here. Okay, if theta is non-trivial, for example, P, you can look at what the previous comments and remarks are giving. So take, for example, two elements. Phi1 is translation by 1, and then you rotate by P. Symmetries of R3, R3 being the universal cover of E theta. you take a second element that is going to be just 2 times phi1. We already saw this example earlier, right? Then this set is invariant by conjugation by the fundamental group, simply because the whole fundamental group is just Z. It's an abelian group. Or by pi1 of x, sorry, pi1 of your manifold, your non-compact flat manifold, which, by the way, is just nothing mysterious. So you can apply the conclusion because star is satisfied. So star is satisfied. So you do get an elementary F structure on and actually there is a T2 action given by phi1 and phi2. T2 induced by phi1 and phi2. So I invite you to imagine what everything is doing. And again, phi1 is proportional to phi2, but by the rule that I tried to describe earlier, they generate a 2-dimensional set of isometries. And in particular, you have a T2 effective action on your manifold. All right, so that's the point of view of having isometries on the universal cover. From certain isometries, you create an elementary F structure. Now I want to translate all of that in terms of geodesic loops. And it's pretty simple. It's just that geodesic loops in your original manifold, they lift to isometries in the universal cover, right? So let me write it explicitly. One can translate everything that I said using the language of geodesic loops. You can translate everything in terms of geodesic loops inside your original flat manifold XL. In other words, given geodesic loops that I'm again going to call phi1 and phi-r, included in this abelian part of the fundamental group. If star is satisfied, then you get an elementary F structure. Which is going to be a torus action on a cover with certain properties. Up until now, I'm not still showing that there exists such a collection of loops such that star is satisfied, but this is the case, and this is a theorem of Cheeger Gromov. That the theorem tells the following. So can be satisfied, the star condition can be satisfied by an explicit procedure, which is by taking loops which in some sense have small length and small holonomy. Phi1, phi-r, phi1, phi-r, sorry, as the geodesic loops at your point, any point that you fixed in advance, with small length and small holonomy. And this is very imprecise. small holonomy. Small here only depends on the dimension. Small length compared to the injectivity radius, and small holonomy in absolute term. Let's see. Let me make a comment. So given a flat complete manifold, you can find a lot of different elementary F structures. You don't need necessarily to go through this procedure. But what I'm saying is that by Cheeger Gromov proved that by looking at this explicit way, so looking at certain loops, which are small in some sense, you get automatically an elementary F structure. And why is that useful? It's because it's a kind of algorithm to get an elementary F structure near a point. It's useful because it picks this algorithm picks for you an elementary F structure. You don't need to think. And I'm not going to show how this is done because it's a little bit tedious. But I'm just going to explain why this is useful. This procedure useful. So in the near future, we're going to take a general case, so a manifold with bounded sectional curvature. And the injectivity radius is going to be microscopic. What you want to do is to blow up the metric at your given point P, so that the injectivity radius is going to be lower bounded on a large region. A large neighborhood, large meaning for the new metric that you blow up, the blow up metric. Large neighborhood of P. Then by the usual theorem of Cheeger, because the injectivity radius here is lower bounded, and when you blow up, you preserve the condition that the sectional curvature is between -1 and 1. When you look at this large neighborhood, it's going to be very close in a pointed sense to a flat complete manifold. Complete manifold. So automatically, by the algorithm that I mentioned earlier, that I described earlier, you get an elementary F structure on this flat manifold, and that means you get an elementary F structure near the point P on the scale of injectivity. So it carries automatically an elementary F structure. And right, so let me summarize what you did. For flat manifolds, we know we have an algorithm to give you an elementary F structure. And you have this blow up argument that suggests that you at any point, you can find a nice elementary F structure. Now what we want to do is to glue these elementary structures together to form a global F structure. Glue together these elementary F structures. So we're going to define F structure now. But before that, is there any question? Okay, so let's continue. So let's define F structures as follows. It's defined by the following data. First, you consider finite cover by open sets U alpha of M. By locally finite. So just finite. Finite cover open sets U alpha. And each U alpha admits an elementary F structure. Structure, which I remind you just means there exists a finite covering space of U alpha, and there exists an effective action of a torus. Of a torus TK alpha on U tilde. Okay, that's just it. And moreover, you want these different elementary F structures to have some kind of compatibility condition. Compatibility condition is satisfied. If you have two of these open sets where you have an elementary F structure with non-trivial intersection, then there exists a U tilde alpha beta, which is a common covering of U alpha, U beta on the intersection part, such that the action of the torus TK alpha and also the action of the torus TK beta, they all lift to actions on this common larger, like bigger covering space. So they lift to actions by the same torus, same tori. Okay. And moreover, either you can embed one torus in the other or vice versa. And here respects the action, the inclusion respects the action. What does it mean? It just means you have a bunch of open sets. On each open set, you have this virtual local torus action. And if you look at two of these open sets, you look at the intersection, this intersection has a very big covering space on which the two different torus actions lift, and they're all compatible, meaning one action is a sub-action of the other torus, or vice versa. So that's the most general definition, but in our mind, all we need to, for example, imagine is something like this. For example, you look at the product of T2 times maybe 0, 1, and U1 is going to be given by T2 times 0, 2/3. U1 is given by T2 times 1/3 1. These are two open sets. On each of these open sets, you have clearly an elementary F structure. For example, on U, you have the natural T2 action, which is a free action, an effective action. And here you have, say, an S1 action. You just take any S1 in the torus, and you get an S1 action. And the union of the two gives you a very nice F structure because one of the action is included in the other action in a natural way, right? An F structure. So this F structure is not elementary because you have two open sets in your covering, U1 and U2. Right, so that is the definition of our main object today, which is F structure. Let's see. So given an F structure, you can talk about this notion of orbits. The orbits are going to be essentially, locally you have a torus action, so the torus action has an orbit. Such an orbit is going to be called an orbit for the F structure. So the F structure is said to be of positive rank if the orbits of the F structure have positive dimensions. So in all the examples that I'm going to consider, all the F structures are going to be of positive ranks. If you check the orbits are never a bunch of points, they're all positive dimensional. Yeah, so you can think of F structures as just being a bunch of local torus actions that glue together in a coherent way. Now the main theorem, one direction of the main theorem due to Cheeger and Gromov is that there exists a dimensional constant, which is very small, such that for any Riemannian manifold such that the sectional curvature is small, is bounded by 1, and the injectivity radius is small everywhere, then the smooth manifold M carries an F structure of positive rank. Of positive rank. So this is the first theorem that is very general, that applies to any thin part, and that gives some structure on it, right? And I emphasize that the definition of an F structure is something that is completely smooth differential. You don't need to talk about the metric when you define an F structure, right? Because you're just looking at local actions by tori. And so the notion of S structure does not depend on any metric. Remark. Definition of F structure doesn't need any metric, doesn't need Riemannian geometry. Even though, of course, it comes from Riemannian geometry. Let's see. I'm not going to prove that theorem because it's going to make everybody fall asleep. including me. So I'm just going to sketch it, I think. Question. Did I wrote? Oh, yes. Thank you. It's a positive number. Yeah. It's otherwise it doesn't make sense. Oh, yes. All right. So how do you prove this theorem? Actually, you're almost there, right? Because again, you start with a manifold with very small injectivity radius. By a blow-up argument, locally you can already find by this algorithm I described an elementary F structure. And all that remains is to try to glue these F structures in a coherent way. The previous algorithm plus blow-up argument give near any point an elementary F structure, and you want to glue them in a coherent way. To glue these together to get a nice F structure, you use the geodesic loops that Cheeger and Gromov want to consider. So these geodesic loops of small length and small holonomy. So the length of the loop is small, and if you look at this holonomy, it is also very small. So at any point, you associate those loops. And remember that those loops automatically define an elementary F structure. So if you have 2 points, you have, well, 2 collections of geodesic loops. There's the geodesic loops. And the main thing that remains to be checked is that if x is close to y, then there exists a natural inclusion of one family into the other family, or vice versa. First family into second family, or vice versa. So once you have this lemma, then it's pretty, I should say, convincing that you can find an F structure. It's because you have this automatic procedure that associate to any point a bunch of loops. These bunch of loops give you an elementary F structure, and this lemma gives you that this bunch of loops varies nicely when you vary the base point. And this is the end, more or less, of the proof of the first theorem of Cheeger and Gromov. And what's interesting is that it's a kind of if and only if theorem. So there's a converse to that theorem, the existence of F structures. And that's the second main theorem of today. Cheeger-Gromov, that says the following. So conversely, if you start with an F structure of positive rank, structure of positive rank, then there exists a family of metric, continuous family of metrics that are collapsing. The sectional curvature is bounded, the injectivity radius is going to 0. In other words, F structures of positive rank automatically gives you a metric that collapses. And conversely, if you have a metric that is very collapsed, then you can find an F structure of positive rank. Let me give you a maybe more precise version. So in fact, if your manifold has bounded sectional curvature and small injectivity radius, small enough so that the first theorem applies, then there exists a continuous family starting at G. So GT here is as above, so it's a collapsing family. And moreover, you start at G. So the idea is that if you have such a metric that has small injectivity radius, you can apply the first theorem, and the first theorem gives you an F structure of positive rank, and this F structure of positive rank is somehow almost invariant by your original metric, so you can change it a little bit, and then you can apply the first point. So in the remaining maybe 20 minutes, I want to start talking about this term because it's an important result in collapsing theory. You have the structural part, but you have the construction part. One thing to pay attention to is that here the sectional upper bound C depends on G. So it really depends on it. It's not something that you can make uniform, at least in this version of their theorem. Okay. Let's try to show this converse to the first theorem. The idea of proof is to apply a kind of elaborate version of the killing field rescaling trick. So I'm going to give you some examples. It's also going to be a sketch of a proof, not a real proof, but the idea is to apply the field rescaling trick but in a more subtle way. Let's start with the most, let's start with the easiest case where you only have one open set and one elementary F structure on that. And we'll see if we can apply this rescaling trick. That would be very good. So consider this case of an elementary F structure, but such that you want to impose an additional assumption, which is that the local torus action is free, such that if you find F structure confusing, just think of torus action. Really, it's enough for that proof. Okay. In the sense that the torus orbits torus orbits, they all have the same dimension of the given torus that is given by the F structure. Same dimension as the torus given by the F structure. So we say that the elementary F structure is polarized. This is the name. Structure is polarized. Again, you can think just of the simplest case of torus action, and being polarized just means that the torus action is free. It doesn't fix any point. In that case, well, this action gives you locally at least a killing field that is nowhere vanishing. I mean, a family of commuting killing fields that are nowhere vanishing. So you can apply the rescaling trick, no problem. You can apply by rescaling these orbits, these torus orbits by delta square, and by exactly the same argument as the example I showed you last time, the curvature is bounded, the injectivity radius is going to 0. So you have whatever you want. That's the easy case, because first we're considering only one elementary F structure, and moreover, you're assuming this strong condition that the local torus action is free, meaning that you're polarized. But under this condition, then it's easy, right? A slightly less easy case is when you have multiple elementary F structures, but still you impose that each elementary F structure is polarized. So if the F structure is made of many elementary F structures that are polarized, together, then you would like to apply the rescaling trick to each of these elementary F structures and try to somehow use some kind of cutoff functions to localize this construction. And then you take the sum of all these contributions, and you hope that you get what you want. So in vague term, before I give you an example, an explicit example, let me just say that you want to just apply the rescaling trick to every elementary F structure that you have in your F structure. And that is possible because each of these elementary F structures is polarized. Use cutoff functions arguments. So to illustrate that case where you have an F structure with, for example, two elementary F structures with different kinds of polarized elementary F structures, let me go back to this previous example, if you remember, of the torus times a segment. So for example, 0, 1, and with that metric, so say the metric that you start with is the flat one, and let U1 be T2 times 0 to, okay, 2/3, and the U2 the other part. And remember, we're defining the F structure by saying that U1 has this T2 action, it's endowed with this T2 action, and U2 is endowed with an S1 action, the S1 being, say, one of the circles in the T2. Say first S1 in T2. Then, okay, it's obvious that you can rescale, say, by T2 in U1, and then in U2, you can rescale by the S1 action, right? But how do you glue these two kind of collapse together? At the end of the collapse, you want something such that on U1, basically everywhere, the T2 is very, very small, while on U2, only the first S1 in T2 is very small, okay? This is what we would like to do. The collapse P with respect to that particular F structure. Actually, here you have a very explicit way of seeing that. You just put a metric on your whole manifold, three-dimensional manifold called G delta, such that G delta is, let's see, it's going to be okay. So the whole manifold with this G delta metric is going to be isometric to a product of a very small circle with S1 cross the interval endowed with a certain metric H delta, and the H delta is going to look like that. So okay, it's H delta is a metric on the surface S1 cross 0, 1, and you want this right side to be of size 1. You don't want to move the fiber. You don't want to move the size of the circle, but you want the size of this circle to be very small. Because remember, in our F structure, you have this T2 action, so and on that side, you have an S1 action. So on that side, you just want to collapse one fiber. On this first open set, you want to collapse the whole torus. And how is that possible to find such a metric H delta? Well, it's possible because you can construct it explicitly, but the point is here. The sectional curvature is, say, +1, and then the boundary on the left is isometric to a very small circle. The boundary on the right is isometric to a circle of radius 1. One essential remark here, important remark here, is that the diameter of this surface has to go to infinity, in fact, because you cannot guarantee that you have bounded sectional curvature, bounded diameter, and this part having injectivity radius going to 0, while this part has injectivity radius not going to 0, because of theorems of say, Cheeger. So what I'm going to say here is that this collapsing sequence, this family of collapsing metric has diameter going to infinity. And this is not something that is an artifact. It has to happen, right? It has to happen. If you have an F structure, you want to collapse the elementary F structures, and then you want to glue these elementary F structures together so that the total metric has bounded sectional curvature, and injectivity radius going to 0, then the diameter has to go to infinity. So I think I'm going to finish on that. And next time I will try to finish this proof by talking about the most difficult case. The most difficult case is when, okay, you have a F structure with many elementary F structures, and some of the F structures are not polarized. Then there's a lot of problems, and I will give only the main ideas of why you still can hope to apply a version of the rescaling trick. So let me just write a last remark, which is this diameter thing. When collapsing metric with an F structure, in general, you will have to, in fact, make the metric very long. So we need to the diameter of G delta going to infinity. So even though the injectivity radius is going to 0, and the sectional curvature is bounded in these constructions, the diameter is going to infinity. And so it's not even clear that, the volume is going to 0. And as a matter of fact, it is not true in general. So this is what I wanted to talk about today. Next time, I'm going to, again, finish this converse theorem. And also, I'm going to probably start talking about N structures, which is a generalization of F structures. So thank you for your attention.
Thank you, Antoine.